Hello, my name is Jonas and welcome to this video about the lonely runner conjecture. I will be showing you my take on the problem, and to my assistance here I have developed a program in Java to calculate and further demonstrate my thinking around this problem. If you happen to already be familiar with the problem, then you can skip ahead 1 minute, or if you perhaps want a refresher on the problem, then feel free to stay a while and listen. So, the lonely runner conjecture is an unsolved problem in mathematics that says if you have a circle-shaped path with a length of 1 unit and k amount of runners running around it, where the runners have different velocities, does there exist a time t for every runner when the runner is lonely? And the definition of lonely is that the distance of a runner has to be at least 1 divided by k from each other runner, where 1 being the circumference of the circle. So let's say k equals 2, then the conjecture states that there exists a time t where any given runner is 1 divided by k, which is 0.5 in this case. So 0.5 apart from the other runners, or runner I should say, for this example. As you can see here, my program passed because the requirement for this runner to be lonely is fulfilled. It's very easy to see that this will always be the case for 2 runners, but for values bigger than 2, it gets harder to prove that that's always the case. Now, the conjecture has been proven up till k equals 7, so for 7 runners with different velocities, there exists a time t for each runner where that specific runner is lonely, but for bigger values than 7, it remains unsolved. Naturally, the case where k equals 8 is the case I started to think about and test around with. I got interested in this problem at first because I found it interesting to think about how long it takes for 2 different velocities to be a distance s from each other. And this can easily be calculated by taking the distance and divide it with the difference in the 2 velocities. This is something I call delta v, and this is what my take on the lonely runner conjecture revolves around: the difference in velocity and the ratio of differences in velocities. I'm now going to run my program once more with these velocities, and the program will then first calculate and find the first time t when the runner is lonely. I will go over the calculations that are being done, or rather the method, which the program and my proof revolves around a bit later. After the program has calculated this, it starts an animation like in the previous example. In this test run, the green runner is lonely at 1250 milliseconds, as you can see. The program will then pause and continues to run after 3 seconds. And you can also switch to the other runners, like so. With these example velocities, all runners are lonely at the same time, and therefore the program pauses at the same time. So, now I will present my method of calculating and checking whether a certain runner is lonely at some point. Usually the first time t for a runner to be lonely can be found by taking 1 divided by k, or 0.125 in this case, where k equals 8, and divide it with the smallest difference in velocities of the other runners. But then one can ask oneself, when is this not the case? Let's call the slowest delta vs, and let's also introduce a variable I, which equals any positive integer. If the runner isn't lonely at that exact time where t equals 0.125 divided by delta vs, there has to be another delta v with a value of bigger than delta vs times 7 plus 8 times I, and less than delta vs times 9 plus 8 times I. If there is such a delta v, then in order to find the time t when the runner is lonely, assuming there is one, we need to take any integer I, 0.125, and divide it with an unknown delta v. For the general case, this can be written down as 1 plus 8 times any integer I divided by k, and divide this with delta v. So, this is how I've been looking at this problem. I realized it's a way to formulate a proof by contradiction. For a runner to never be lonely at the time t equals an integer I, 0.0125, divided by a delta v, there must be another delta v that prevents it from being lonely at that specific time. And this must be the case for every different delta v for a certain runner. Now, looking at the correlation between 2 different delta v, Let's call them delta Vx and delta Vy. Delta Vx being the difference in velocity between a runner x and a runner z, and delta Vy being the difference in velocity between a runner y and a runner z. We can use this ratio of the two delta V values to see what the distance is between a runner y and runner z at the time t when the distance between runner x and z is a certain distance. An example of this is delta Vx divided by delta Vy equals 0.5. And then if we take 0.125 times 0.5, it equals 0.0625. And what this tells us is that when delta Vy has a distance of 0.125 between the runner y and z, delta Vx has a distance of 0.0625 away from runner x or z. Observe that it's the decimals that are important. 0.0625 is less than 1 divided by k, and therefore the runner is not lonely at this time t when a distance of delta Vy equals 1 divided by k. So using the ratio of delta V values, I managed to construct a proof that shows how a certain runner is never lonely if you allow there to be k plus 1 runners instead of k runners. So this doesn't disprove the conjecture, but I will go over it anyways because my proof argues that k plus 1 runners is the minimum amount required for a runner to never be lonely. So taking the case where k equals 8, and remember the smallest delta V is called delta Vs, and we have this variable I, which is any positive integer. Then with a total of 8, or k delta V, with the values of delta Vs times 8, delta Vs times 7, and delta Vs times 6, and so forth until delta Vs times 1, then the runner is never lonely. To better understand this proof, I want to explain more thoroughly what we're actually looking for. We're looking for what's ratios of two different delta V times an integer I plus 0.125 that has decimals less than 0.125 or bigger than k plus 8 times I minus 1 divided by k and less than k plus 8 times I plus 1 divided by k. This is the position required for the runner never to be lonely. So, let's define period as p, which we will use to describe how long it takes a ratio between two delta V to return to the same decimals. The amount of periods for a certain ratio is its fraction. Halves have a period of 2p, thirds have a period of 3p, etc. After we go through this first case, it will hopefully be a bit clearer. So 2p is when the period equals 2, when delta Vx divided by delta Vy equals halves. An example of this is where delta Vx divided by delta Vy equals a half, so 0.5. And then if we take 0.125 times 0.5, it equals, as we have already seen, actually 0.0625. And if we take 1.125 times 0.5, we get 0.5625. And if we take 2.125 times 0.5, it equals 1.0625. And another example is where delta Vx divided by delta Vy equals 7 divided by 2, which is 3.5. And then we have the following values right here. As can be seen, the decimals returns after 2 periods. This is the case because 1.125 times 0.5 just simply equals 0.125 times 0.5 plus 0.5. And 2.125 times 0.5 is equal to 0.125 times 0.5 plus 0.5 times 2. So what we need to note from this is that the value where delta Vx divided by delta Vy equals a half prevents the runner from being lonely at the time 0.125 plus 2p. And when delta Vx divided by delta Vy equals 7 divided by 2, it prevents the runner from being lonely at 1.125 plus 2p. And the combination of the two leads to the runner never being lonely, because 0.125 plus 2p contains every even number, and 1.125 plus 2p every odd number, and together they contain every positive integer. There's also values for delta Vx divided by delta Vy where the period equals 1p. And this is the case where delta Vx divided by delta Vy is a product of 8. So an example of this is where delta Vx divided by delta Vy equals 8 divided by 1, which is 8. And then if we take 0.125 times 8, it equals 1. And 1.125 times 8 equals 2. And it follows this pattern. So if delta Vx divided by delta Vy equals a product of 8, then the delta Vy only requires delta Vx to never be lonely. And this is the case because, as in the last one with 2 periods, 0.125 plus 1p contains every positive integer there is. Now, in order to prove that the 8 delta V with the values of delta Vs times 8 and delta Vs times 7 and so forth, until we reach delta Vs times 1, result in the runner never being lonely, we need to look at the periods from 1p to 8p.
So here are the values. If you would like to have a look at these values, then I will upload my proof as a PDF document in the description, in which you can study the values and read a similar, but perhaps more detailed version of everything I'm going over in this video.
Now, by observing these computations, we will be able to see that the delta V values result in the runner never being lonely. For simplicity's sake, we can say that delta Vs equals 0.1. Then the other values of delta V will be 0.2, 0.3, and so forth until we reach 0.8. And as has been shown, if delta Vx divided by delta Vy equals 8, which is the case for 0.8 divided by 0.1, this leads to the runner never being lonely at the time t, where I, which is a positive integer, plus 1 divided by k, divided with 0.1. And for delta V equals 0.2, we need to have a look at delta Vx divided by 0.2. If we have delta Vx divided by 0.2 equals 0.5 and delta Vx divided by 0.2 equals 3.5, the runner is never lonely at any time t equals I plus 0.125 divided by 0.2. And this is the case that we have these values of delta Vx. So 0.1 divided by 0.2 equals 0.5. And 0.7 divided by 0.2 equals 3.5. Using the same principle, we can check the other delta V, and we can then conclude that the runner with a velocity 0.1 is never lonely, because for every delta V, there exists no such time t equals I plus 0.125 divided by any of the delta V where the runner is lonely. Here are the rest of the delta V. So with this method I will present my take on a proof of why having these 8 or k different delta V, like in the previous example, is the minimum amount required to prevent a runner from ever being lonely. Let's start off with some undeniable facts. There has to be a maximum of 7 different delta V, because there are a total of 8 or k runners if we are to stay within the rules of the conjecture, that is. And another fact is there has to be a certain delta V that are bigger than the others, meaning we need values of delta Vx divided by delta Vy that are less than 1, where delta Vy is the biggest delta V. If we look back at the values from 1p to 8p, we can see that there is no combination of delta Vx divided by delta Vy values less than 1 that fills every integer until 8p. Conclusively, we need a combination containing 7 different delta V, where delta Vx divided by delta Vy equals less than 1, where delta Vy again being the biggest value of those delta V, and a period p is equal to or bigger than 8.
Now I want to go over some characteristics about values of the ratio delta Vx divided by delta Vy. The first one being why there's no odd number for delta Vx for an even value of delta Vy that prevents the runner from being lonely at time t equals p divided by 2 plus 1 divided by k times delta Vx divided by p. For any even value of delta Vy, for example 22, so the period equals 22, there is no odd number for the delta Vx that prevents the runner from being lonely at the time p divided by 2 plus 0.125 times delta Vx divided by p. So with 22 as an example, there is no odd value for delta Vx where the decimals of 22 divided by 2 plus 0.125 times delta Vx divided by p makes it so the runner in question is lonely at that time. And it's because the decimals are always bigger than 0.125 and less than 0.875. And this holds true for values where delta Vy or p are bigger than 4, and delta Vx is an odd number, which I will now demonstrate with some examples. Even numbers of delta Vx are irrelevant because if both delta Vy and delta Vx are even, the ratio of delta Vx divided by delta Vy can be simplified further. So, with 22 as an example again, we have 22 divided by 2 plus 1 divided by 8 times 1 divided by 22, and this will always be bigger than 0.125 and less than 0.875. And we can see that that's the case fairly easy if we simplify it a bit. So 22 divided by 2 plus 1 divided by 8 equals 11.125. And we have this times 1 divided by 22. And this can be written down as 22 divided by 2 times 1 divided by 22 plus 1 divided by 8 times 1 divided by 22. And this equals 22 divided by 44, which is 0.5, plus 1 divided by 176. So it's very easy to see here that this will be bigger than 0.125 and less than 0.875 because it's 0.5 plus 1 divided by 176, which is a very small number. And you can see that this pattern follows with all the odd numbers. So with 3 as an odd number, we have 11.125 times 3 divided by 22, which is right here 1.517 and so forth. So as we can see for the period 22, odd numbers can't reach the requirement where the decimals are bigger than 0.125 and less than 0.875 because it can only range between 0.5 plus 0.00568 and so forth to 0.5 plus 22 divided by 176 to 0.5 plus 0.125. Now, for even numbers, on the other hand, we have 1 plus some even number, x, divided by 22 times 8. So we have 22 divided by 2 plus 1 divided by 8 times 2 divided by 22, which equals 44 divided by 44, which equals 1, plus 2 divided by 176, which is a very small number. So you have 1 plus a very small number. So that will be in range of the requirements because it's less than 0.125. And this is the case for all even numbers here. Another characteristic I noticed while looking at the different ratio values of delta Vx divided by delta Vy is that when the value is an odd number, or more specifically when the period is an odd number, then to fill every number it needs a delta V which equals 8 or a product of 8. If we have a look at the odd periods like 3, 5 and 7, we see that a certain positive whole number plus 0.125 times all different third fractions like 1/3 or 2/3, etc. always equals a certain 8th fraction. Let's have a look at 3 and 5 to get a better understanding of this. For 3p, if we have 1.125 times a third, it equals 3 divided by 8. And if we have 1.125 times 2/3, it equals 6 divided by 8. And then if we have a look at 1.125 times 8/3, it will equal 24 divided by 8, which is 3. So 8 divided by 3, or 16 divided by 3, etc., a product of 8 basically divided by 3, is the only third fractions that, when multiplied by 1.125, equals a whole number. This means that there's no other values that prevents the runner from being lonely at 1.125 plus 3p. If we look at the period 5, 3.125 times 1/5 equals 5 divided by 8. And 3.125 times 2/5 equals 10 divided by 8. And then we have 3.125 times 8/5, which equals 40 divided by 8, which is 5. So naturally I try to develop a proof that only 8 or some product of 8 divided by an odd number is the only value that's result in a whole number, and also why a certain number plus 0.125 times fractions of an odd number always equals some 8th fraction. The reason why only 8 divided by an odd number is the only value that leads to a whole number is fairly easy to see. If we again look at 3p and 5p, and let's use x and y as positive integers, then we have x times x divided by 8 times y divided by x equals y times x divided by 8, which can be seen right here. So 9 divided by 8 times a third equals 1 divided by 8 times 9 divided by 3, which equals 1 divided by 8 times 3. And 9 divided by 8 times 2/3 equals 2 divided by 8 times 9 divided by 3, which equals 2 divided by 8 times 3. When y equals 8, we can write it as x times x divided by 8 times 8 divided by x, which equals x times x divided by x, because the two 8's cancel each other out. So we have 9 divided by 8 times 8 divided by 3, which equals 9/3, which equals 3. So now let's look at why a certain number plus 0.125 times fractions of an odd number always equals some 8th fraction. Again, using x and y as positive integers. As you may have noticed, for an odd number x, it seems like x times x divided by 8 is the number that when multiplied by 8 divided by x equals some positive integer. This holds true for odd numbers less than 8. For odd numbers greater than 8, it is always x minus 8 times y times x when x is bigger than 8 times y. For the first odd number greater than 8, which is 9, 9 minus 8 equals 1, which leads to 1 times 9 equals 9. So 9 divided by 8 times 1 divided by 9 equals 1 divided by 8. And 9 divided by 8 times 8 divided by 9 equals 9 divided by 9, which is 3. So finding this number is resemblant to looking for the greatest common divisor between two numbers. For example, if we have 9, which equals 8 times 1 plus 1, the last number is the number to be multiplied with the odd number x if x is greater than 8. And it should then be equal to 8 times y plus 1, where y is positive integer. There's a simple reason to why it's that specific reminder that when multiplied by the odd number x will equal some product of 8 plus 1. As previously mentioned, for an odd number x which is less than 8, it follows that x times x equals some product of 8 plus 1. If you take an odd number x which is more than 8, it will always have the same decimals as another odd number less than 8. So to find what product of 8 plus 1 that equals an odd number x multiplied with the remainder of x equals 8 times y, where y is the biggest possible whole number that can be multiplied with 8 and be less than x, we write it as x minus 8 times y divided by 8 times x. This multiplied with 8 equals x multiplied with the remainder of x equals 8 times y, where y is the same as in the last bracket. An example here is where x equals 15. Then we have 15 minus 8 times 1 divided by 8 times 15, which equals 7 divided by 8 times 15, which is 15 times 7 divided by 8. So for x equals 15, x minus 8 divided by 8 times x times 8, which should equal x times x minus 8, which is clearly true if we simplify the left side a bit. So we have x minus 8 divided by 8 times x times 8, which leads to x times x minus 8 times x, which equals x times x minus 8. So 1 plus 8p divided by 8 is every positive whole number plus 0.125, like 1.125, 2.125, etc. 1 plus 8p equals 1 divided by 8, 9 divided by 8, 17 divided by 8, etc. Some number contained in 1 plus 8p can be divided by an odd number x, and this is true for every positive odd number of x. Now I want to go over why it's not possible to only have even delta v values or periods. And I'm going to do this by using my program here. So another part of this program is a part I created which generates data about ratios of delta v, x and y, and essentially checks the values like we did earlier, and it will then write down to a text file at what points the different delta v values prevents the runner from being lonely. So I will now generate data for only even values of delta v, just to easier show how it's impossible to completely prevent a runner from being lonely with only even values for the periods. It has now generated data with even delta v values up to 50. So I will now open up the documents generated here. So first of all, with only even delta v values, the periods appearing here aren't always even, because, as we have established, it's the fraction of the ratio of two delta v values that decides its period. And if we now have a look at the period 50, which is the maximum delta v in this case, the first ratio is 48 divided by 50, which will result in a period of 25, because both delta v can be simplified further by dividing them by 2. So the period becomes odd anyways. But if we scroll down here and take the next one, period 48, then we have an even period, which is 24. This value here is 46 divided by 48, so that's okay since both are even. But then if we have a look at 46, the period will be odd again. And the rest of the generated data obviously follows the same pattern, as you can see, where every other period is even and every other is odd. So there's no possibility for there to only be even periods.
Now, since that's the case, an odd period is required, and that leads us, as we have seen, to there having to be a delta v that equals 8, or a product of 8. Now I want to show that having delta v values that, instead of being 8, has values resulting in a period with the value of another product of 8, can't prevent the runner from being lonely. As we have seen, when we have an odd period, which will always be the case at some point, a delta v that equals 8 or a product of 8 is required. And to tie together this proof, I'll have to show that having only values with a period of 16, for example, instead of 8, doesn't prevent the runner from being lonely. Here's some visual calculations of the ratio of delta vx divided by delta vy that will hopefully help with understanding this. I have also shown that having only values resulting in a period that equals a product of 8 that's bigger than 8 can't prevent the runner from being lonely because of the fact that there has to be an even value for that to happen at time t equals p divided by 2 plus 1 divided by k times delta vx divided by p.
Now, this last characteristic or pattern for ratios of two delta v values is a very encompassing and, well, a broad pattern. And it says that for a positive integer bigger than 1 and less than an odd number x, a close enough approximation of the ratio needed to prevent a runner from being lonely at the time t equals I plus 1 divided by k divided by delta v is found by the following calculations. So we have x times 1 divided by I and divide this with x. If we go over 7 as an example here, then for I equals 2, then for the period 7, t equals 2.125 divided by delta v is only lonely when the ratio has a value of approximately 7 times a half divided by 7. and this is 3.5 divided by 7. Rounded off, this equals 3 divided by 7, which is the ratio required. For I equals 3, then for when t equals 3.125 divided by delta v is only lonely when the ratio has a value of approximately 7 times a third divided by 7, or at approximately 7 times 2/3 divided by 7. For some of the cases where x isn't particularly big, only one of those values will be the one required, and for this case it's where 7 times a third is divided by 7, which rounded off equals a ratio of 2 divided by 7. To show exactly why this holds true, I will have to refer to my PDF document in the description, where a more detailed section about this can be found. The document is done with LaTeX, and as I said, I will make sure it's in the description of this video if you would like to have a look at that. So, with combining all these characteristics or patterns of the ratio of delta V values, then we can formulate this proof that k plus 1 runners is the minimum amount of runners required for a runner to never be lonely. Again, a more detailed version of how exactly this proof ties together is found in the PDF document, but the conclusion of these patterns that I've gone over will lead to there having to be delta V's that are spread out in a manner that leads to there having to be 9 or k plus 1 runners in total for a runner never to be lonely. So, if you somehow made it to the end of this video, I of course want to just thank you for taking your time, and I hope you found this somewhat thought-provoking. Do feel free to leave some feedback, whatever it might be, and again, thank you for watching. Goodbye.